Is it visible, Abhishek ji?
Yes, you can start.
Okay, so thank you. So myself, Professor Manish Patil, Assistant Professor in TKT Varnanagar, Kolhapur. I'm going to present my slide on the best on the chemical reaction equilibrium for the CEEE program and IIT Delhi. So we are going to cover the chemical reaction engineering thermodynamics. In that, I'm talking about the reaction equilibrium, how it is going to be reached, and what is the importance. Then the importance of the grip free energy. Then also I am going to discuss the
I
equilibrium
am signing
constant.
out.
Okay. So also
I
I'm
am
going to discuss the importance of the reactor design and the importance of process optimization, because this particular chemical reaction equilibrium would be important in the design of reactor also, and also it would be going to get the information regarding the process optimization. So in the introduction, I'm going to discuss what I mean by chemical reaction equilibrium. In a chemical engineering, we are not only interested in the whether the reaction can occur, but how far it will go. In industries, the raw materials cost money, energy cost money, and separation also cost money. Therefore, understanding equilibrium help us to answer what is the maximum possible conversion, what will be the final composition of the reactor, and is it economically feasible to run the reaction. So our emphasis would be on the whether the chemical reaction equilibrium going to uh, give the certain information. So the kinetic tell us how far fast reaction occur, but the thermodynamics tell us the limit. So chemical reaction equilibrium deals with the study of the final state attended by the reversible chemical engineering. So obviously we have said that equilibrium depends on the temperature, pressure, and composition. So in the introduction, I'm going to discuss that the fundamental question that the many students think that chemical reaction go on completion, but it rarely go. It doesn't true in the most of the cases. Chemical reaction do not always proceed to the completion. So at the state of equilibrium is reached when the forward reaction equals to the rate of reverse reaction. So there would be a certain equilibrium. There would be a certain molecules are going to go to the forward direction and certain molecules are going to be backward direction. So net flow would be zero, though the concentration may vary, but the net flow in the both direction would be zero. So thermodynamics predicts the maximum achievable conversion, and obviously that equilibrium depends on the temperature, pressure, and the composition. So equilibrium doesn't mean a reaction stop. Molecule continue to reaching the both direction, so only net change occurs would be equal to zero. So we are going to discuss standard state concept. So thermodynamics always works on a reference condition because of the absolute values of properties like Gibbs free energy, which cannot be measured. So what would be the standard state? The standard state is a hypothetical reference condition used for the comparison and calculation. So we can say the standard state definition, the pure solid and liquid activity would be equal to 1. Their concentration does not change significantly. For the gases, standard state of would be equal to the standard pressure is equal to 1 atm. For the solution, standard state would be 1 mole per liter. So standard state does not mean actual operating conditions. So it is used to define Gibbs free energy and equilibrium constant. This simplifies the thermodynamics expression. So this would be the Gibbs free energy. So Gibbs free energy is an important thermodynamic property for chemical reaction at the constant temperature and the pressure. So for definition, the G would be calculated as G is equal to H minus Ts. So here G would be the Gibbs free energy, H would be the enthalpy, T would be the temperature, S would be the entropy, that would be degree of disorder. So it would determine the direction of the chemical reaction. So criteria would be the simplest, that delta G is equal to less than 0, it would be spontaneous reaction. Delta G greater than 0, it is a non-spontaneous reaction. Delta G is equal to 0, it would be the equilibrium condition. So reaction can be endothermic, but it could be a spontaneous. a reaction can be exothermic, but it could be a non-spontaneous. The next that we are going to discuss is the standard Gibbs free energy, that is delta G. So delta G defined as the when all reactant and products are in the standard state. So delta G is why it would be important, because it gives the information about reaction tendency. It directly relates the equilibrium constant. So fundamental relation that would be going to correlate would be delta G is equal to minus RT into ln K. It is one of the most important equation for the solving the most of the problem. So where R is a gas constant, T is absolute temperature, K is a equilibrium constant. So large negative delta G, that means large K that produces the product's dominance. So when there is a delta G is a positive, it would be a small K, and it would be also reactant is going to be dominating. Then we are going to discuss reaction equilibrium. So at equilibrium, the forward reaction rate is always equal to the reverse reaction rate. So concentration remains constant, but at microscopic level there would be change in molecules. So pressure temperature also remains constant. So equilibrium is a dynamic, not static. So molecular reaction do not stop. Only observable macroscopic properties remains constant. So we can relate this analogy as number of people entering in the classroom and number of people leaving, same number of people leaving the classroom at the equal rate. So we can say this is a reaction equilibrium. Then we are going to discuss law of mass action. That is very important mathematical expression for the calculation of equilibrium. For the reaction A, for the reactions A giving A plus B giving B, going to give a product PQ with stoichiometric ratio small p and q. Then the equilibrium constant can be calculated by the concentration of product of P, concentration of product of Q, that would be also molar concentration upon molar concentration of A and molar concentration of B. So where PQ RS are the stoichiometric ratio, small pq are AB, then capital PQ are the product molar concentration, AB are the molar concentration of reactant. So powers are equal to the stoichiometric coefficient. Only species whose concentration change is included. So solid and pure liquids are also excluded. So K value depends on the temperature. Changing initial concentration doesn't change the K value. Then we are going to discuss equilibrium constant. The equilibrium, why we are learned to what mean by equilibrium constant. K does not tell us the reaction speed. K does tell us about the how far reaction proceed. So when it would be expressed in a molar concentration applicable mainly in the reaction in a solution. When K is a very large value, then product favored reaction. When K is a very small value, then definitely reaction favored the reaction. Then pressure based equilibrium constant, sometime for the gas phase reaction, the instead of concentration we can express this terms in the partial pressure also. General expression would be Kp is equal to partial pressure of the product divided by partial pressure of reactant. So it would be related Kc using the ideal gas law equation. So Kp could be calculated, or the relation between Kp and Kc would be equal to Kp is equal to Kc into RT raised to delta N. So delta N is a number of moles in the gaseous product divided by moles in a gaseous reactant. Then the reaction coordinate. So reaction coordinates tell us the extent of reaction. Also we can also it could be tell the progress of a reaction. So it represents the reaction progress and the change in number of moles proportional to the stoichiometric coefficient. So the I is equal to 0 at the start of the reaction. Change in the moles is proportional to the stoichiometric ratio. At equilibrium, psi value reaches the fixed value. So it will be useful for the material balance, and it also useful for the help in the calculation of equilibrium composition calculation. Then the reaction quotient, that will be Q. that also used for predicting the direction. Q has the same form of K, but uses current concentration. The current concentration means concentration at any point, not just equilibrium position. It will help us to find the direction of a reaction to reach the equilibrium. When Q is equal to Q less than Q, the reaction proceeds forward direction. When Q is greater than K, reaction proceeds to the backward direction. When Q is equal to K, system would be at the equilibrium. Now we're going to discuss the point lead charter's principle. It would be one of the qualitative prediction tool. When the system is at equilibrium is disturbed, it responds with the minimize the disturbance. So disturbance could be in terms of change in concentration, change in pressure, change in temperature. So it would going to give the information regarding the direction, not magnitude. Temperature can be affect the K value. The pressure concentration do not affect the K value. So we are going to study the effect of temperature. Effect of temperature on the equilibrium. So for the equilibrium constant change with temperature, it can be predicted by the Van 't Hoff equation. It could be calculated. Ln is K2 by K1 is equal to minus H by R into 1 upon T2 minus T1. So these are the K2, K1 value are the equilibrium constant for the forward reaction and backward reaction at the temperature T1, T2. So for the endothermic reaction, when delta is equal to greater than 0, the K increases with temperature. For the exothermic reaction, delta H is equal to less than 0, K decreases with temperature. So temperature change alters the equilibrium constant. So temperature is the only factor that changes the equilibrium constant. So now we are going to study effect of catalyst. Most of the common misconception is that catalyst lower the activation energy and also it increase the rate of both forward and backward reaction. But actually it does not change the equilibrium constant. It does not change the equilibrium constant. It helps to reach equilibrium faster. Now Gibbs free rule. Gives phase rule that system analysis tool that F is equal to C minus P plus 2. C is the components, P is the number of phases involved in the system, then F is a degree of freedom. So it helps determine the number of variables that can be independently changed. It would be also useful in the multi-phase reacting system. Then the industrial importance, why we engineer care the equilibrium constant or equilibrium concept. The most important are it is used in the ammonia synthesis, the Haber process. Then also it could be used for the reactor sizing. Then also it could be used to selection of the operating conditions. And also it would be one of the important parameter for the economic optimization or the process economics. Industry often operate at the non-equilibrium conditions to balance. So we have to determine the yield rate cost. That are the most important concept or the important part that we need to understood for the industry point of view. In a summary, we can say equilibrium limits the maximum conversion. Then Gibbs free energy predicts the reaction direction. Equilibrium constant quantifies the equilibrium position. Lee-Tarcher principles explain the equilibrium shifts, how it is going to shift. Then essential for the chemical engineering application. So equilibrium constant or equilibrium would be useful for these 5 things. So these are the references. Thank you. Abhishek ji, can I, if any questions you can ask, or I will stop my sharing.
Yeah, you can stop.
Okay. Okay, can I leave this session particular?
Yes, you can leave. I'll stop
Okay, thank you.
the meeting now.
Great. recording. Okay, thank you.